All right, guys, welcome to lesson 5.6. We're going to be talking about concavity. So by the end of the day, you should be able to tell me what concavity is and also what the concavity of a given function is, as well as what a point of inflection is and where that's at on a given function. Okay, so we're going to talk about concavity is the big topic and point of inflection is a subtopic to that. So let's begin. So first of all, let's review what does this mean here, f double prime of x. It's the derivative of the derivative, which means it's the rate of change of the rate of change. In other words, it tells us how fast the slope is changing. So if f double prime is positive, that means that f prime is becoming more positive or less negative, because it means that f is increasing. F prime is increasing. So I'll say that again. You might want to add that little note to your notes as well. If f double prime is positive, that means that the slope of the slope is positive, which means that f prime is increasing. And therefore, if f prime is increasing, it's either becoming more positive, if it's already positive, because that's one way you can increase, or if it's negative, it would have to be becoming less negative in order to be increasing, right? And if f double prime is negative, that means that f prime is decreasing. And if f prime is decreasing, that means that f prime is becoming, this is a typo, f prime is becoming less positive. That's one way you could be decreasing. Or you could be becoming more negative. So those are the two ways that f prime could be decreasing. Now, it also tells us, the second derivative also tells us how quickly f prime is changing. Instead of it's, I'm going to put f prime is changing. It tells us how quickly f prime is changing. The bigger the number, the greater the magnitude of that number, the more quickly it's changing. Okay? So that is what the second derivative is and what the second derivative tells us. So now, if f double prime is a positive number, then we said that means that f prime is increasing. Now, look at these slopes. These slopes are becoming, they're positive and they're becoming more positive. Like this slope down here in the bottom left, I would say maybe that's like 1/4. I would say that this slope here is about 1, and this slope looks like it might be 4/1. So it's becoming a bigger and bigger positive slope. And as you put those slopes together, as you can see, you get a bend in an upwards direction. Now let's take a look at this other one over here on the right side. Over here, this looks like maybe it's a -4. This would be maybe a -1 and a -1/4. So starting on the left, we started negative, but it's becoming less negative as we move to the left. So the slopes go like this, right? And when you have that, you also have a bend in an upwards direction. Even though the graph is moving in a downward direction, the bend is in an upward direction. And that's what we call being concave up. So we'll say that again. If f double prime is positive, that means that f prime is increasing, which means that either it's becoming more positive or less negative in the slope. And when that happens, you end up with concave up curves, curves that are bending in an upward direction. Okay. Contrary-wise, if your second derivative is less than 0, or if your second derivative is negative, that means that f prime is decreasing. So for this graph here, we have a slope that is starting positive, but it's becoming flatter, so it's becoming smaller. So it's becoming less positive. Whereas over here, we're starting off with a slope that's kind of negative, and then as we move to the right, it becomes more and more negative. But in either case, you guys can see the curve is bending in a downward direction. So it's concave down. So once again, when the second derivative is less than 0, or in other words, negative, that means the derivative, or the slope, is decreasing, which can happen in one of two ways, but either way, your graph is considered to be concave down. Okay, so the point of inflection is the point at which a curve changes its concavity. So I would encourage you for a minute to pause the video and kind of just trace with your finger, or maybe just mentally in your mind, where you believe this curve is concave up. And then I want you to trace with your finger where you believe it to be concave down. And then after that, I want you to identify the point at where it changes. So concave up, I would say, is about from here to about here. And then I would say that concave down would be like from here to here. And so the point of inflection would be right here in the middle, where we change from being a concave up graph to a concave down graph. And so this point right here in the very center would be the point of inflection. Now, since this side, the green side over here, is concave up, that means that f double prime is greater than 0. It also means that the slope is increasing. Now that's confusing because it looks like the graph is going in a downward direction, right? But remember, I'm not talking about the y values, I'm talking about the slope. Like up here, the slope's really negative, then a little less negative, and then a little less negative, until finally it reaches right here where it's 0. So if the graph starts off with a really negative slope, and that negative slope starts becoming less negative, it's technically increasing. Okay? And then over here on the right side, we have a concave down graph. Right? Which means that the second derivative is less than 0, or another way of saying that is that the derivative is decreasing. Starts off with a slope of 0, and then it's kind of negative, a little more negative, and a little more negative. It gets more and more negative, so the slope is decreasing because it's becoming more negative. Now, if the green side is a positive, is greater than 0, if the green side's second derivative is greater than 0, and the red side's second derivative is less than 0, then what would the second derivative be right here? Well, what's between greater than 0 and less than 0? Equals 0, right? So that is what a point of inflection is. It's the place where your function changes concavity. So here's a summary of what we've discussed so far. So what does f double prime of c tell us about the graph of f of x at any given point x equals c? Well, if the second derivative at that point is greater than 0, then that means that the graph would have to be concave up at that point. If the second derivative is less than 0 at that point, then that would mean that the graph has to be concave down at that point. And then finally, if f double prime of c equals 0, or as we'll see later, if the second derivative is undefined, then that means that point possibly could be a point of inflection. The only thing that would be standing in its way is that not only does it have to equal 0 or be undefined, but there's a couple other criteria that have to be in place. One of those being that the concavity actually has to be changing at that point. But for now, that's a good enough summary for where we're at. So here's some examples of some points of inflection. As you guys can see, from here to here is concave up, whereas from here to here is concave down. And so that point where I've got my little tangent line there is the point of inflection. Here we've got concave down. Here we've got concave up. And so once again, where those regions meet is the point of inflection. And then finally, we have concave down is on this side here, and concave up is on this side here, and where they meet is a point of inflection. So there we have it. Now I want to point something out to you here. this is one of the situations where your second derivative would be undefined. Why? Well, because this is a tangent line. The tangent line can tell you what the first derivative is. So what would be the first derivative at that point? Well, since it's a vertical tangent line, it's undefined. And if your first derivative is undefined at that point, then you can't take the second derivative of it and all of a sudden get an answer. It's also going to be undefined at that point. So that is a case where you can have a point of inflection where it's not where the second derivative doesn't equal 0. Instead, the second derivative is undefined. Okay. Now, why is it that just because the second derivative equals 0 or it doesn't exist, why does that not necessarily have to mean that it's not a point of inflection? Well, for instance, consider this one here. Right here, f prime does not exist. And if f prime doesn't exist, then f double prime doesn't exist. But just because f prime doesn't exist, f double prime doesn't exist, that doesn't mean that this is not a point of inflection. Why is this not a point of inflection? This is not a point of inflection because even though the second derivative, d and e, does not exist, the concavity does not change at that point. Okay, so take a look on this graph here. To the left, it's concave down. But look on the right. The right is also concave down. It went from concave down to concave down. That is not a point of inflection. So that's one situation where even though the second derivative does not exist, it's still not a point of inflection. Now, here's another one. Since this is a hole, that would mean that f prime of x does not exist. And if f prime of x does not exist, that also means that f double prime of x does not exist. And furthermore, not only that, but to the left of that point we have concave up, and to the right of that we have concave down. So why is this one not a point of inflection? Well, the reason why is because there's no point there. You can't be a point of inflection if there's no point that exists there. So since the function doesn't even exist at that point, C cannot be a point of inflection. Okay, so yes, it changes concavity at that point, and yes, we have one of our criteria. The second derivative doesn't exist, but that doesn't necessarily make it a point of inflection because it also has to be defined. So as we saw on the last page, if f double prime doesn't exist, like here, that is a point of inflection. But just because f double prime doesn't exist doesn't mean that it is a point of inflection. There's actually another one. As you guys know, if f double prime equals 0, that's another situation where it could be a point of inflection. So here's another case here. Like suppose I told you guys this. Well, the first derivative would be 4x cubed, and the second derivative would be 12x squared. Now, where does this function equal 0? For what value of x? At what value of x would my second derivative be 0? It would be 0 at x equals 0. So, but when you graph this function, it looks like this. It almost looks like a parabola, but a little bit flatter at the bottom. So, at that point, we have f double prime of x. We could actually be more specific and say f double prime of 0 equals 0, right? So, does that make it a point of inflection? F double prime equals 0 like it's supposed to. And the point exists like it's supposed to, but what's the problem? The concavity doesn't change. It's concave up, concave up. They're the same. So the concavity has changed. So that leads us to, what are the full requirements for being a point of inflection? The function would have to change curvature at that point, and the function has to actually exist at that point. If those two criteria are satisfied, then you're good to go. I think on your notes I had an extra point there about there not being a cusp. That's not true. You could scratch that out. All we need is for the curvature to change and for the function to be continuous at that point. All right, so let's go ahead and take a look at example 1 here. We want to identify where f double prime of x is equal to 0. We want to identify where f double prime of x is greater than 0. And we want to identify where f double prime of x is less than 0. Now, when the function is less than 0, well, not the function, but when the second derivative is less than 0, that means the graph would be concave down. So where on this graph would it be concave down? It's definitely concave down here, but here's the tricky part. Some of you guys might be tempted to go down to here, but that's not true. Because as you guys can see on this little interval right here, it actually starts to bend in an upward direction. It's here that it's bending in a downward direction. Somewhere in here it stops and it switches. So actually, I would say that it's concave down from here, probably up to about the middle of that line, because the rest of that would be concave up, which I'll use green for. Okay, so I would say from there to the green would be a concave up section, and the purple would be a concave down. Another place where this graph would be concave down is probably like from here to, maybe I might have went too far, maybe from here to here. And then I would say that it's concave up for the rest of it. Okay? So, now how can you tell? Well, whenever you have a situation, just so you guys know, where a graph is transitioning from being concave down to concave up, usually the transition point is going to be somewhere in the middle of where the downward hook connects with the upward hook. Okay, so there we go. So now that we have that, the points where those two regions are connecting, like here, here, and here, those are all points of inflection. So as we said before, this is concave down. This is concave up. And these are points of inflection. Okay, so first of all, let's go ahead and let's identify our points of inflection first. Now, points of inflections are points. There's 3 of them, and they're x values. So what's the x value of this first dot right here? I would say if this is 0 and this is -2, -1 would be in the middle. So this is a little bit to the right of that. So it's probably a little bit more than -0.5, but let's go ahead and just say -0.5. We're estimating here. Now this one's a little bit easier. That point of inflection is 0. And how about this one? Well, once again, I'd say 1 is here. This dot's a little bit more to the left of the center. So once again, I'd say positive 0.5. So those would be my points of inflection. So where is the graph concave up then? Now, that's not a point. That's a collection of points. That's an interval. So the entire green region there is concave up. So we can assume that it just keeps going on here forever. So from the left, which is a -infinity, up to that first point of inflection, which is -0.5, it's concave up. And it's also concave up starting here at 0 until we get to the last point of inflection at 0.5. And then we would say that it's concave down in all the purple areas. So the first purple area starts at the first inflection point, negative 0.5, and then it stops at 0, that inflection point. And then the last purple region starts at a positive 0.5, and after that it just goes off into infinity to the right forever. So that's how we're going to be estimating, and I said estimate because they're not happening in exact spots, but we're estimating the values of x for which the second derivative is 0, the second derivative is greater than 0, and the second derivative is less than 0. In other words, they're really just asking us to find the points of inflection and the places where it's concave up and concave down, right? So that's our first example. All right, so here's a student practice for you guys. So pause the video here and see if you guys can find where the derivative is greater than 0, the second derivative, where the second derivative is less than 0, and also where the second derivative equals 0. When you unpause it, you'll see the solutions. So if your answers are close to mine, you might be right. We're just kind of eyeballing this a little bit, but let's go ahead and begin here with the first one. Let's find where the second derivative is greater than 0. All right, well, I would say that from here to here is concave up. And because of that, I said that the first interval is from negative 10 to 3. I would say another place where it's concave up is starting here to here. And therefore, I said from 6 to 8. Next, where is the second derivative less than 0? In other words, where's this function concave down? I would say this is concave down, which would be from negative 3 to 3. And I would say that this is also concave down, which is from 3 to 6. The last thing that we need to do is we need to find some points of inflection. Now, the points of inflection are located at those places where the colors switch from purple to green, like right here, for instance, and so I put x equals 6. But you'll notice that I didn't include this one. Why not? Because for a point to be considered a point of inflection, it has to be continuous at that point. And so this is not considered to be a point of inflection. Yes, the concavity changes at that point, but the point itself doesn't actually exist. So that one will not be listed as a point of inflection. All right. So let's move on to example 2 here. In example 2, we're going to pull away from graphs and we're going to start looking at equations instead. So for example 2, it says, for each function below, find the points of inflection and determine the intervals for which the function is concave up and the intervals for which the function is concave down. All right, cool. So the first thing that we're going to do is we're going to find the second derivative. So let's do that. So to do that, the first thing I need to do is I need to find the first derivative. And then after that, we can find the second derivative by taking the derivative of the first derivative. All right, so that's the first thing you want to do is find your second derivative. The next thing you're going to want to do is set it equal to 0. And we're also going to want to find where is it undefined. Just like we do with critical values, you do the same thing with points of inflection. You want to find where g double prime is undefined, and you also want to find where it equals 0. So for the equals 0 part over here, let's go ahead and divide everything by 12. Add 4 on both sides. Take a square root, and you end up with plus and minus 2. So I end up with 2 possible points of inflection. They may be points of inflection, and they may not be. Okay. Also, we want to find out, are there any places where g double prime is undefined? Well, g double prime is a polynomial, so there are none. Okay, and by the way, technically, I guess we should have done that over here. The real first thing you want to do is find any discontinuities of g. I forgot to do that, sorry. Because if g has a discontinuity, then that's not going to be a point of inflection anymore. But for g, that's a polynomial, so once again, there are none. So step 1, see if there's any discontinuities. Step 2, find the second derivative. Step 3, find where the second derivative is 0 and where it's undefined. Okay? Okay, cool. So now, these are possible points of inflection. I say possible because, okay, fine. Remember, in order to be a point of inflection, the function has to be continuous there, which it is because g has no discontinuities. It has to it also has to be a place where the second derivative is either 0 or undefined, which it is. But something else has to happen there. What else has to happen there is the curvature has to change. We have to actually make sure that it's concave, it changes from concave up to concave down, or vice versa, concave down to concave up at those points. All right. Now, if we had some points over here, we'd have to test these ones also. But guess what we're going to do now? We're going to go back to that old familiar number line test. Only this time, we're not doing it with critical values, we're doing it with possible points of inflection. And we're not plugging it into the derivative this time, but we're plugging our test points into the second derivative. Okay, so let's pick a point on the interval from negative infinity and negative 2. Let's plug in negative 3. And how about from negative 2 to positive 2? I'll plug in 0. And then from 2 to infinity, I'll plug in 3. So we're going to plug those into that second derivative, which was 12x squared minus 48. All right, so mental math here. If I plug 3 in, that's going to be 9. 9 times 12 is 108. 108 minus 48 is going to be 60. So this one comes out to be 60. And since we're squaring it, negatives don't matter, so this one's going to give me the same answer. And if I plug in 0, this is going to cancel out and leave me with negative 48. So what that means is that on the interval from negative infinity to negative 2, my graph is concave down. And then on the interval from negative 2 to positive 2, my graph is concave up. And then on the interval from 2 to infinity, my graph is concave down. Oh, I think I'm saying that backwards. My bad. This is positive, so it should have been concave up. My bad. Sorry about that. And then on the next interval, it's concave down because it's negative. And the next interval is concave up. So that's what it would look like there. Okay. So now we're ready to answer the question. Where is this concave up at? G is concave up on the interval of negative infinity to negative 2, and also from 2 to infinity. So we're going to put both of those on there. Where is it concave down? It's concave down right here. So that would be from negative 2 to 2. And then finally, where are the points of inflection? Okay, well that would happen anytime we're switching from purple to green, or in other words, concave up to concave down, or from concave down to concave up. So, question. is the original function g continuous at -2? Yes, because polynomials are continuous everywhere. So it's also continuous here. So that's the first criteria. Second criteria, does the concavity change at that point? Are we switching colors? Yes, we are. So both of those are points of inflection. So we have a point of inflection at -2, and we have a point of inflection at x equals +2. Okay, so let's review the steps one more time. So step 1, make sure your function doesn't have any discontinuities, and if it does, make sure you know where they're at, because if you end up with a possible point of inflection, you know not to use it if it turns out to be a discontinuity, because points of inflection can't be points of discontinuity. Next, we want to find the second derivative. Next, you do another number line test. With the second derivative, though. That's new. We've always done our number line test with the first derivative, but now we're doing it with our second derivative. Okay? Actually, that was step 4. Sorry. We'll get to that. Step 3 is to find possible points of inflection by doing your second derivative equal to 0 and your second derivative is undefined. Look for those points. And then step 4 is where you do the number line test. Step 5, write your answer, but when you're done, you want to make sure that they're actually points of inflection, right? A point of inflection has to be a point where the original function is continuous, and it has to change concavity. Okay? So that's the process. So let's go ahead and have you guys try one of these. So let's go ahead and we'll do number 1 like a guided practice, and then we'll do number 2 like a student practice. So guided meaning we'll do it one step at a time. So go ahead and pause the video here and do your first step and see what you guys get. When you unpause it, I'll tell you what the answer is. So the first thing is to determine the continuity. So it's continuous everywhere. So we don't need to worry about any discontinuities because it's a polynomial. All right, go ahead and do step 2. When you unpause the video, you'll see the solution. Step 2 is to find the second derivative, which you see here. So go ahead and pause the video here and do step 3. When you unpause it, you'll see the solution of that. So this is where we set the derivative equal to 0 and solve. So to solve it, you're going to factor out a common factor. I chose to take out a -6, and then I factored the trinomial. And if you set this one equal to 0, you get -½, and if you set this one equal to 0, you get 1. So we've got 2 possible POIs right there. And then for the second derivative, you also want to see where it's undefined, but once again, since this is a polynomial, there are no places where it's undefined. So we only have 2 possible points of inflection. All right, pause the video here and do step 4. All right, so here's step 4. I picked, there's my number line. My possible points of inflection are -½ and 1. So I've got 3 intervals I need to test. So I'm going to pick -1 from the first interval and plug that into the second derivative. And I don't know about you guys, but I'm very tempted always to come back and plug it into the original by accident. Don't do that. You're plugging it into the second derivative. So when you plug it in there, you get -12. So when your second derivative is negative, that means your graph is concave. The graph of y is concave down at that point. I plugged in 0 and I got a +6. So since it's positive, it's concave up on that interval. And then I plugged in 2 for the last interval and I got -30, so it's concave down again. All right, so go ahead and write your answer for step 5, please. Okay, so we're concave down here, which is which is this interval. And we're also concave down here, which is that interval. We are concave up here, which is that interval. And since there's no discontinuities, we know that the dot does exist here at these points. And we also see that the color switches at those points. So we are changing from concave up to concave down. So since both criteria are met, both of those qualify as points of inflection. All right, so that's a guided practice. Why don't you guys go ahead and do number 2 now on your own from beginning to end. When you unpause the solution, you'll see all 5 steps up here for you to compare your answer to. All right, guys, so here is your final solution for that particular problem. And if you want it, go ahead and pause the video here and study it, but I'm going to clear it at this point. And I think that does it for our lesson for the day. So, till next time, see you then.